Hello everyone. Thanks a lot to attend this section to listen to our talk. The talk of this paper is the sparse data-driven mesh deformation. This is the joint work of Ling-Xiao, Yu-Kun, and Zhang, Ling-Xiao, and Professor Leif Kobbelt. And firstly, let's review the related works. The shape representation and the shape deformation representation is very related with the shape deformation. Sometimes the shape deformation could be used to preserve the representation and to satisfy the user constraints. Very previous work and the very pioneering work such as the Laplacian coordinates, torsion-based gradient field reconstruction, and dual Laplacian and deformation gradient. These work are mainly based on the deformation gradient, and it defined on the memory neighborhood. It is the translation invariant representation. When we rotated the mesh model, the deformation representation will be changed. To deal with the rotation, other deformation representations have been presented to deal with the rotation, to make it rotation invariant and translation invariant, such as the very pioneer work of linear rotation invariant representation from Leif and the freeform motion. These works are freeform rotation invariant work. However, they are not very easily to make the deformation with the positional constraints. Only positional constraints. Sometimes they use some other constraints such as the rotation. Now let's review the deformation. There are lots of mesh deformation methods, such as the Laplacian style mesh deformation and the as rigid as possible deformation. As rigid as possible is a very famous style to deform the shapes. This is Olga's work, and also some recent work of the smooth enhanced as rigid as possible. This work is good to keep the local detail and is able to deform the shape with only handles, with only the positional constraint. However, these methods are not data-driven methods. Nowadays, we know that given the data, we learn the data, we will make the deformation has a much better result, much better effect. But this state of the art method doesn't considering the data-driven. So to use the data-driven, and also there are some other works to use the data, to learn the data to make the deformation have much better result, such as the very famous work of the mesh IK. But the mesh IK is based on the deformation gradient. We know that the deformation gradient is not rotation invariant, so the mesh IK is not easy to handle the exemplar shapes with very large scale deformation. And for the deformation, data-driven deformation with the edge and dihedral angles, these features such as the edge length and dihedral angle is the rotation invariant. But the problem is that it cannot do the extrapolation. It is unreasonable to have the edge length to below 0. And also recently there is another work from our group is the rimmed representation. This representation could do the extrapolation and the rotation invariant and is designed for the general shapes. However, it's the solving algorithm is not have the explicit formulation, so the solving is not so efficiency. Now let's to look more about the motivation. The motivation is that when we handle two shapes, we want to design here we want to design data-driven deformation. Firstly, we need to use the we need to design a shape deformation representation that could handle very large scale deformation, such as these two examples. The lines were rotated multiple cycles. If we blend them directly with the deformation gradient, we could not get the good result. This is because that there is ambiguity for the deformation gradient. When we make the interpolation of the deformation gradient, we will get the wrong result. This is because deformation gradient. This is because the deformation gradient is ambiguous for large-scale rotation. The desired shape is much reasonable like the right figure in this slide. So we want to develop a deformation representation that could handle very large-scale deformation, but is not have this ambiguous. Besides the deformation representation, another motivation of our work is to design how to blend the deformation basics. For traditional idea, to blend the deformation basics is using the linear blending. From this figure, we can find that the linear blending is the deformation space is the convex hull of this yellow area. However, we know that not all the yellow area have meaningful shapes. So the key idea here is that we want to use some sparsity to find a much tighter and compact deformation space. The compact deformation space will generate much reasonable shape deformation. So here, how to employ the sparsity to make the deformation space from this convex hull to this compact and tighter space is another motivation, is to use the sparsity. So how to design the mesh deformation? How to design the mesh deformation could handle very large scale deformation. If we look at this cycle rotates multiple cycles. It has very large deformation. But we use if we zoom out the shape, we can find that although the deformations are very large, but in the local area, the deformation is not so large. The deformation is smooth, is continuous. So this gives us an idea. We could use this smoothness and continuous to find the consistent deformation representation. And also we find that if we want to make the deformation space to be much compact, the L1 regularization makes the sparsity, makes it as sparse as possible, will help to find the compact deformation space. So here we will tell much more of the methodology and the technical details. Firstly, we will tell more the deformation representation, as consistent as possible deformation representation. Now let us look at the mesh. We find the mesh is that if we zoom out the figure, we will find that the mesh is composed of multiple triangle. And the deformed mesh is the transformed triangle. So the deformation could be viewed as the collection of the translation of the different different triangles. So we could use the least square to estimate the deformation gradient in each varying neighborhood of the vertex, and we can decompose the deformation gradient into the rigid rotation and the scaling part. And for the rigid rotation, we know that the rigid rotation is including two variables. One is the rotation axis, another is the rotation angle. So the ambiguous of these two variables is that the rotation axis will have two directions, and the rotation angle also have multiple cycles. So here we get the ambiguous. So the idea here, we want to explicitly to express the large-scale rotation. So we want to know which rotation axis is correct and which cycle of the rotation angle is correct. So here we want to find the solution space, solution in this solution space. The solution space is like that. The rotation axis has two directions, and the rotation angle has multiple cycles. We want to identify the unique image of the rotation representation. So here we want to find the map. And let's thinking about the initial finding. We find that the rotation, the large scale deformation in the local area are smooth and continuous. So we can use that findings to formulate some mathematical formulation. It's something like that. It's something like this. Let's think about the two vertices. Two vertices in the in one edge. Here is the edge, and here is the two vertex. Here is the rotation angle, rotation direction OI and OJ. We want the OI and the OJ to be as consistent as possible. That means that the angle between OI and OJ should be as small as possible. So how do we formulate this? We can use the dot product. Because the OI and OJ are unite vector, the dot is larger. It means that the angle between them is smaller. So we want to make the deformation in the adjacent vertices to be as consistent as possible. The angle between the rotation axis should be as small as possible. Then their dot product should be as large as possible. So we make the dot production here. We move dot production, the variable OI or OJ means the direction. If equal to 1, is this direction is correct, and equal to the minus equal to the, if OI equals -1, it means that the direction should take the opposite direction. The opposite direction. So here is the formulation. We want to find the correct direction of the rotation axis. This is the integral programming, and we can solve this integral programming by the commissal from the Leif Kobbelt's group work. And when we get the rotation direction, and next we want to find the cycle. The principle is also that the difference between the two adjacent vertices should be as small as possible. So we just minus these two angles. The left one is from the rotation angle of the vertex Vi, and the right one is the rotation angle from the vertices of Vj. So we want the difference to be as small as possible. So here we use the squared to measure the difference. And from the previous optimization, we get the rotation angle, rotation axis here. And next, we want to get the period. And then also use the commissal, we can get the period. And now we get the as consistent as possible deformation representation. And then we also know that we want to find some deformation basics. We use the previous state-of-art research to get the basic deformation from using the this formulation, and the input is as consistent as possible feature. And then we use this sparse decomposition method. We could get the deformation basics like this. This is from the Cardiff's work, and the sparsity is defined on the spatial region. And then the novelty of our sparsity is here. We define sparse on the weight. The weight is sparsity help to use as small as basic as possible, then use the deformation space is compact, which we told before. And here is our optimization with this sparsity here. And this one is the SGP feature deformation features, as consistent as possible features. And given the shape collections, we get the SGP features, and then we use the sparsity. We could make the deformation space to be much compact, and this could be solved by the ADMM optimization method here. Much more detail could be found in the paper.
Given the SAP feature, and we want to do the data-driven deformation, the key idea of data-driven deformation is to blend the SAP feature with the weight. So the key idea is to solve the weight and the new position together. Here we involve a new energy. We can look at the energy. The TIW is the weighted sum of the feature, and we want to minimize this energy to get the final position and the final weight. So look at this energy. The typical idea to solve this energy is using Gauss-Newton method. First, we do the Taylor expansion of the TIW, and then we get the Taylor expansion. Then we take the Taylor expansion to this least square. Then this will become a least square problem, and it is very good that the left matrix AL will be fixed during the optimization. So solve this linear equation several times, we can get the final position and get the final weight. This is the Gauss-Newton method. And what about adding the sparsity? If we add the sparsity, the algorithm will become a little different. It's like this. It will added the extra L1 sparse term on the weight. So here we will use the algorithm of lasso. This will become the lasso problem. We will use the ADMM method to solve it. So this will, besides solving the position sparsity will involve 2 extra steps, including the shrinking step and the variable updating step. After these steps, finally, we will get the new position, new weight, and with the extra sparsity term.
Now let's find the result. We find that this representation is very robust to the noisy. Given to skip model with noisy, we can do the interpolation. We can find that this interpolated model is very reasonable. And also it could handle very large scale deformation. We just rotate the cylinder multiple period, and the interpolation one is also in the reasonable shape. This is another deformation. This is the data-driven deformation. Given two exemplar models, we could drag the handles to move multiple cycles. We can find that our method can have very reasonable deformation models, but other methods are failed. The mesh IK is failed for the representation, and the Wapler method could not get a reasonable result. And this model is show that the sparsity is quite helpful. Given the sparsity, when we drag the handles, only a small basics is activated. The good is that we drag the model is very robust. Only a small part of the model will be moved. This good property is from two sparsity. One sparsity is the sparsity on the weight, like this figure. We can find that the weight is sparsity. And another is from the sparsity deformation basics. And here is the we can with the help of sparsity we can do the multi-scale deformation. And this figure shows that with the sparsity, the deformation result is much robust and much local. And the left one, the traditional data-driven method, is not so robust. If you drag the point, all the models will be moved together. And this is good from our method. This is the observation study to show that the sparsity is helpful to let the deformation in the local area. And this is the evaluation of a different parameter. It shows that our selection is in the good manner. And also we show that the time efficiency of our method, we can find that give the much more deformation component. Our method can also run very fast, and other previous method will run very lower when the components is becoming much more. And here is some technique details how we make the deformation in the much efficient manner. Here is the video with the multiple scale deformation. We have different basics. Some of the deformation basics are defined on the facial area, and some defined on the whole shapes. So we could just drag the handle in different area. Different basics could be activated. This is benefited from the sparsity constraint. So we could do the multi-scale deformation. And the future work, I think that this give a good deformation representation. We could use this A cup feature to represent the shape, and with some neural network, we could encode and decode the shape. And actually, we just do that. You can find much more work with the A cup feature, and we use the A cup feature to develop much more neural networks to make the geometry processing in the intelligent way. Thank you. Please view our web page to find the paper and to find much more related research works. Thanks again.